Good afternoon, ladies and gentlemen. I want to thank CT to invite me to give this presentation. My name is Tiejun Cui from Southeast University, China. So this is my topic. I want to speak microwave metamaterial antennas. So I will give background and motivation on this topic, and then I will mainly introduce two types of metamaterial antennas. The first is anisotropic zero-index metamaterial antennas, and the second is a metamaterial lens antenna, and followed by the conclusion. So for the background, for the antennas, actually, antennas are everywhere, and Professor Yablonowicz gave a review on this, on the basic concept of antenna. Actually, for the antenna, we have two constants to design or to use the antenna. So the first factor is the geometrical and mechanical factors, and the second one is electrical factors. For the geometric and mechanical factors, we're concerned about the size, the weight, and the shape of antennas, and also sometimes concerned about the power capacity of antennas. For the electrical parameters, there are a lot of measures for antennas. For example, the gain, directivity, the bandwidth, reflection coefficient, the efficiency, beam width, side lobes, and the beam forming, beam steering, and polarization coupling, and a lot of factors. And a big concept on antennas is very similar to the diffraction limit in imaging. That is, there is a gain limitation in antennas. That is, for any antennas in nature, the maximum gain cannot be larger than this limitation. So this, as Professor Yablonowicz mentioned, that lambda square over 4 pi is equivalent area of isotropic radiation. So this maximum gain means that the real size aperture area A over this isotropic equivalent aperture area. So this is a maximum gain. That means no matter what kind of current distribution, you cannot obtain a gain larger than this limit. So this limit is only obtained when the current is uniformly distributed on the aperture A. And also, there is an old saying in the antenna community that there is no free lunch. That means there are a lot of constraints in antennas. For example, there is a constraint in between the gain and the bandwidth. If you want to get a high gain, you cannot get a wide bandwidth. Also, there is a constraint between the gain and the side lobes, and the beam steering angle and the bandwidth, etc. Therefore, what is the motivation for metamaterial to work in the microwave antennas? We know that antennas is very active in the optical frequency right now, but for the in the microwave region, the traditional antennas are very, very mature. The performance of the microwave antenna are also very good. So what we can do for metamaterial in microwave antennas? I think there are 4 steps. The first is how to improve the performance of antennas using the metamaterials. I think this is the basic. This is the basic motivation. If we cannot improve the performance, there is no use for the metamaterial antenna. So the second is how to use metamaterial to build up new concepts or new types of antennas. And the third one is, can we break the constraint of traditional antennas? And the last one is, can we break the limitation of antennas? So in the past years, so a lot of researchers have been working on the small metamaterial antennas, for example, using the resonance to realize the small size antennas, and also to realize artificial magnetic substrate to improve the efficiency and the bandwidth of antennas, and also to reduce the mutual coupling of array antennas in a small size. So, but my presentation will not be focused on the small antennas. The first I want to speak is the anisotropic zero-index metamaterial antennas. For zero-index metamaterial antennas, a lot of researchers like Professor Ingeta Andreas Alou have done a lot of work on zero-index metamaterial. But why we want to start an isotropic zero-index metamaterial? So the first is it is very easy to realize. Second, it is for isotropic zero-index metamaterial, it is easy to make the impedance matching. And the third, there are a lot of new features from the isotropic zero-index metamaterial. And another question is how to make the isotropic zero-index metamaterial. Actually, there are two ways to create isotropic zero-index metamaterials. The first one is we make the isotropic in the Cartesian coordinate system. And the second is a cylindrical coordinate system. The third one is a spherical coordinate. So I will introduce the first two, Cartesian coordinate and cylindrical coordinate. So now we start from a very simple 2D problem of isotropic zero-index metamaterial. So it is a TE problem. The zero index happens in the y direction. That means only in the y component there is one component, either permittivity or permeability is equal to 0. Here we choose mu y equal to 0. So from the Maxwell equation and the dispersion equation, we can easily derive the basic property of such kind of material. Because when mu y equal to 0, so from the Maxwell equation, we know that Ez must be constant respective to x. This is the first conclusion. And the second one is when mu y approaches to 0 from the dispersion equation, we know that kx must be equal to 0, and ky just equal to k0 square root epsilon z and mu x. So this is so from this simple derivation, we conclude that only plane wave propagating along the y direction are supported in the in such kind of Cartesian anisotropic zero-index metamaterial, no matter what kind of sources it is, point source or line source or other kind of sources. So this is a simulation for this anisotropic zero-index metamaterial. For example, if we have a line source, if we have a 2D point source in free space, it will radiate a cylindrical wave perfectly. However, when a point source, 2D point source is radiates in this kind of Cartesian anisotropic zero-index metamaterial, it will radiate directly plane waves. So this is the case when the anisotropic zero-index metamaterial is infinite. For a finite size anisotropic zero-index metamaterial, we notice that when the source is inside radiating, we have two very important features. The first one is from the simulation, we can see that the point source inside the anisotropic zero-index medium, it seems that the source is stretched to a strip with uniform distribution. So this is a very important concept. And the second is from the radiation field, we can see that the wavefront is a plane wavefront, and also the area of the wavefront is larger than the real aperture. So this property makes it possible to create a larger effective area than the real aperture. Then we can it is possible to break the limitation of the antenna gain. But this has not been verified. I just realized this when I prepared the PPT. And this is the experiment we have done in the 2D case for this kind of Cartesian anisotropic zero-index metamaterial. So we realize anisotropic zero-index metamaterial using the SR structure. So we can find the anisotropic zero-index point at the frequency of 8.1 gigahertz. And this is a simulation results and this measurement results. So no matter the shape, what the shape looks like, it always radiates plane waves. This is a measurement result. There is a there is a slight, a big difference from the simulation. I think this is due to the slight loss. We can improve the experiment in the future. So, so that is the 2D case. But for practical applications, we have to realize 3D case. So using the similar idea, we decompose the 3D electromagnetic field to the TE and the TM modes, and then we can realize 3-dimensional isotropic zero-index metamaterial disk. So for the left one, it is for the epsilon epsilon z nearly 0. For the right one, it is mu z nearly 0. For such two kinds of metamaterial plate, when we put the plate to the conventional antenna, we expect that such kind of isotropic zero-index metamaterial plate can improve the gain of the original antenna. So this is an experiment when we put the two plate on a traditional rectangular horn antenna. So these are measurement results. This is with epsilon z near 0. We compared with the sample and without the sample. We can see the beam-wise, main beam-wise has greatly reduced. And this is also true for the mu z component equal to 0. So we can, using the isotropic zero-index metamaterial, we can increase the directivity and decrease the bandwidth, beam-wise of the antenna significantly. Another application of the isotropic zero-index metamaterial is used in a planar antenna. So the antenna we choose is a well-known Veradi antenna, because for the Veradi antenna, it has ultra wide bandwidth. But from the constraint of antenna, the gain of such kind of antenna is not large. So right now, we want to improve the gain of the Veradi antenna without destroying their original good property of wide bandwidth. So this is the design we make for the Veradi antenna. Actually, based on the original Veradi antenna, we didn't increase the size of the original antenna. We just make a isotropic zero-index metamaterial in this open area. Then this is a working frequency around the 10 gigahertz, and then we can make a 1 gigahertz bandwidth to improve the gain significantly. So this is a fabrication sample. So this is a measurement result for the reflection coefficient. We see that after making the isotropic zero-index metamaterial, the ultra-wide bandwidth property is kept. So we can see the reflection coefficient is nearly the same as the original. However, we can improve the gain significantly in the designed frequency band. So the design frequency band is from 9.5 gigahertz to 10.5 gigahertz. We can see within this frequency band, the gain has been greatly enhanced. And also in most area, most region in the frequency band, the gain has been increased. Not so much, but increased in the whole band. Also, to increase the bandwidth of the Veradi antenna for enhancing the gain, we use the graded isotropic zero-index metamaterial. That means we didn't use homogeneous isotropic zero medium. Instead, we use inhomogeneous isotropic zero-index medium, because we can then we can improve increase the bandwidth. So this is a fabrication sample, and this is a measured reflection coefficient. Again, the ultra wideband property is kept, but the antenna gain in the design frequency from 9.5 gigahertz to 12.5 gigahertz has been greatly enhanced. This is a comparison of the gain. So right now the bandwidth has been increased to 3 gigahertz. So from above example, we can notice that using the isotropic zero-index metamaterial, we can improve the constraint of the antenna. We keep the ultra-wide bandwidth, but improve the gain in the design frequency band. So next, I will introduce another isotropic zero-index. It is in the cylindrical coordinate system. That is, if we make an anisotropic zero-index metamaterial in the reading direction, in the rho direction, then we can make another features of antenna radiation. That is, no matter what kind of source is placed inside or inside a ring of such kind of cylindrical anisotropic zero-index metamaterial, all sources will always radiate omnidirectionally. The second is we can realize a spatial power combination using such kind of zero-index metamaterial. So also we make a very brief derivation from the Maxwell equation. So this is the constitute parameters of the radially anisotropic zero-index metamaterial. From the Maxwell equation, when the radial component of mu rho equal to 0, we can easily obtain that the fields are constant along the phi direction. And the second, from the dispersion equation, when mu rho is equal to 0, we can easily obtain the k phi equal to 0 and k rho equal to k naught times epsilon z mu phi. So that means no matter what kind of sources inside, it always radiates a perfect cylindrical wave. And also, so now we take a look at the simulation results. This is a full wave simulation when we put 4-point source inside the anisotropic zero-index metamaterial. So without the isotropic zero-index, it will radiate directionally. We have 4 beams, very apparently. However, when the 4 sources are placed inside the isotropic metamaterial, it will radiate perfectly cylindrical wave. So in this case, different from the planar case, the any sources inside the isotropic metamaterial will crush it to the center to radiate perfectly cylindrical wave. So this is an experimental realization. We still use the SR structure to realize the anisotropic component of the AZI, and this is the measurement results. So in the first case, we put a source in one position apart from the center. We can see this is a measured amplitude. This is a measured phase. We can see a perfect cylindrical wave is observed. This is another position. This is when 2 sources are placed together. Then we notice that all cases perfect cylindrical wave is observed. And another very important feature for this isotropic zero-index metamaterial is that we can make very efficient spatial power combination of 2 sources or multiple sources. For example, when this kind of isotropic zero-index metamaterial, we have 2 sources inside, then we can show that after a derivation, we can show that the total power of the 2 sources will be nearly 4 times larger of one single source. This is easy to understand because, as I said, for this AZI, it crashes all sources to the center of the cylinder. If we have 2 current radiate simultaneously and in the center, then the field will be 2 times larger and the power will be 4 times larger. So this is a measured result verified the conclusion. And also, this conclusion is valid to any kind of antennas. We have 2 line antennas, for example. It has also, we observe the omnidirectional radiation and also the power combination. And this idea can be extended to the fan-shaped radiation, because for the wireless communication system for the B network, sometimes we require the fan-shaped radiation pattern. So using such kind of isotropic zero-index metamaterial, when we put a PMC on the boundary, we can realize any fan-shaped radiation. And also such kind of radiation also have the power combination. Even for the previously introduced Cartesian coordinate isotropic zero-index metamaterial, we still realize the power combination. This is a radiation of single source. This is a radiation of double sources. We can see that the amplitude is 2 times larger than one source. So this is a very good feature for this kind of material. So now I move on the second type of metamaterial antenna. I call this metamaterial lens antenna. In this, for this kind of antenna, I will introduce the planar slide metamaterial lens and the curved surface lens, such as the Lundberg lens, Fisheye lens, Fresnel lens, and also the transformation optics lens. And finally, I will briefly introduce a general metamaterial lens, which can be control both the phase and amplitude of the aperture. So this is the first example of the metamaterial lens initially proposed by Professor Smith's group. Actually, we can use geometric optics method to derive the distribution of the index of refraction to guarantee the phase on the required aperture are equal. Then it can then we can obtain high gain radiation. So this is, in this case, we suppose that the beam will be radiated to the theta direction instead of the normal direction. In such case, we can also derive the required distribution of the index of refraction. So this is a simulation result of the 2D case for the gradient index length. So in this simulation, because from the geometric optics method, we only derive the index of refraction, and there are a lot of choice for the electric permittivity and magnetic permeability to realize the same index of refraction. For this simulation, we choose both epsilon and mu are equal, then both of them equal to n. In this case, the reason we choose this case is that for this case we can get perfect impedance match to the free space, and then we can get very good antenna performance. So this is a required distribution of the index of refraction depending on which direction will the antenna be radiated. So this is the simulation result. So we can see from the simulation result, the wavefront are perfectly planar, and also the size of the wavefront is nearly equal to the aperture size, which means that the antenna have a very high efficiency approaching to the maximum gain of the antenna. So this is a comparison of such kind of gradient index lens with a conventional dielectric lens. For example, when we put a dielectric lens, a Rotman lens in the same horn, we can see the gradient index lens antenna has a much better performance than the conventional Rotman lens, both for the gain and the side lobe. So this is an experiment to verify the 2D flight gradient index lens. So we design such kind of the unit cell to realize the electric resonance and the magnetic resonance in the same time, and then realize a metamaterial with the same epsilon and mu. And the aperture size of the antenna is 12 centimeter. So this is a measurement result for the normal radiation and also for the oblique radiation. So this is a maximum angle to the So next, I want to extend the 2D flat gradient index length to the 3D case because for practical application, we have to use 3D antenna. For the 3D case, if we want to realize broadband property of the antenna, it is difficult for us to use to choose a metamaterial with the same epsilon and mu because that will be a narrow band. So now we only design the permittivity, but in this case we have to design two impedance matching. Okay. Thank you. So in this case we have to design two impedance matching layers to decrease the reflection of the antenna. So for this kind of antenna, we just use a square ring as a unit cell to change the size of the square ring to realize the gradient distribution of the lens antenna. So this is a retrieval distribution of the refractive index n. It changes from 1.1 to 2.3. So this is a fabricated flat lens, 3D flat lens. The flat lens is placed in the front of a conventional horn antenna. We can see this is a measured reflection coefficient. We can see that the antenna works from the 8 gigahertz to 12 gigahertz, covering the whole X band. And the S11 less than minus 14 dB for the whole frequency band. And the aperture size is 9.6 centimeter. And this is a measured radiation pattern. This is for the E-plane radiation pattern. This is the H-plane radiation pattern. We can see that covering from the whole X band from 8 frequency to 12 frequency, the small aperture antenna have a very good far field radiation property. We have compared with the same aperture horn antenna with the same length. We can see that at the 12 gigahertz, the metamaterial slab length antenna can enhance the gain by 6 dB than the original hand. Also, we realize a bigger flat length antenna. So this time it is 25 centimeters. At the 12 gigahertz, the gain can reach 30 dB. This antenna the gain is 5 dB higher than the dielectric Rotman lens. So this is a measured result for the E-plane radiation pattern and the H-plane radiation pattern. So they are very beautiful. And the other kind of lens which can be realized by metamaterial as a surface lens. For example, the basic one is a Lundberg's lens. For the Lundberg's lens, it has a lot of advantage. For example, when we put the feed in on the surface, and then it will radiate high gain to the opposite direction, and also it can realize multi-beam radiations. And however, the Lundberg's lens require a gradient index material inside the sphere. Traditionally, we use discrete layers to realize Lundberg's lens. So the first, it is very expensive, and the second, because they use discrete multi-layers, there is an impedance mismatch between the different layers. And then we can use metamaterial to realize the Lundberg's lens very easily. So this is a 2D case we have done in 2 years ago. These measurement results have very good features. This is a planar Lundberg's lens realized using the complementary I-shaped unit cell. So the results looks very good. And also recently we realized the half 3D Lundberg's lens to make the radiation to the required angle. So for this half 3D Lundberg's lens, we use a simple dielectric particles with different holes to make the gradient distribution of index of refraction. So for this kind of dielectric with holes, we can model it very accurately because this is a full wave simulation. This is a ideal gradient distribution of index. This is a computational simulation. This is a real structure with different holes to realize a gradient index. So no matter it's an internal field or an outside field, they have perfect match. And this is a measured radiation pattern and insertion loss of the Lumber's lens antenna covering the whole KU band. And this is a Maxwell fisheye lens, half of the Maxwell fisheye lens to make a high gain radiation. So for the traditional Lumber's lens, there is a disadvantage. That is, the focus plane, the focus surface is a spherical surface, so it is inconvenient for the array fading or for the multi-beam generation. So Professor David Smith's group proposed a concept of the transformation optics lenses. So they just make an optical transformation to change the spherical surface or part of the spherical surface to a plane. And then when the feed is placed on the plane, then it can radiate the high gain, make the high gain radiation to different directions. So in my group, we realized a three-dimensional transformation optics lens. So this is the original Lumber's lens. We make a optical transformation to transform this spherical surface to the planar surface, and then we still use dielectric with holes to realize the 3D distribution. So, but for this, in our case, to realize the 3D, we just rotate the 2D distribution to 3D. So this rotation is actually has some approximation. It's not exact optical transformation, but the approximation is very good because in the along the cross sections passing the optical axis, they are accurate. So they are accurate, and also only when the cross section very far away from the optical axis, there are some shape change for the plane wave. So this is the design and of the 3D transformation optics lens. So we use two kinds of dielectric with higher dielectric constant and lower dielectric constant to realize the required distribution of N. And this is the measurement results. We can see for the measurement results, the near field measurement, we can see that it is very broadband from 12 gigahertz to 18 gigahertz. And we measured very good oblique radiation of good plane wave. This is the case when the source is placed at the edge of the plane. So it will have the maximum radiation angle. So this is the measured far field radiation pattern, the H-plane, the E-plane radiation pattern, and H-plane radiation pattern. So for this kind of transformation optics lens, it has very good features with high gain, relatively low set lobes. It is valid to do polarizations, and it has a very large radiation angles up to 50 degrees and have a broad bandwidth. And finally, I will introduce a general 3D metamaterial lens. Actually, we can, using such kind of lens, we can control both the amplitude and the phase, because in the previous flat lens and the curved Lumber's lens, fisheye lens, we only can control the phase of the aperture. So the idea is we choose a general 3D lens. This surface is to radiate, is for the radiation, so it can be plane. For the other surface, it can be curved. This curved surface can be used to control the propagation of the rays inside the inhomogeneous metamaterial. So actually, we can derive, we can derive some efficient formulations for the ray tracing using the ray tracing method. For the first interface, we can derive the incident rays and the angle, the incident refraction angle, and also inside the lens, we can derive the differential equation to govern the optical path of the metamaterial. And also, as a second surface, we can derive the refraction angle beta. And also, using this energy conservation law, we can make a link between the aperture distribution, field distribution, and the index of refraction n. And then we can make the design you require. For this example, we just choose the flat lens. The two surfaces are flat surface. And then in this case, we want to design an optimized antenna with the gain and the side lobe. That is the Taylor distribution of the aperture field. So then we can derive, after using the optimization method, we can derive the distribution of the index of refraction. So this is the amplitude distribution. This is a phase distribution. For the phase distribution, it is nearly a constant because the maximum is most of them within 10 degrees. So this is a fabricated new metamaterial lens. So this is a measured insertion loss. We can see very good features, less than 20 dB for the reflection coefficient. And this is a measured radiation pattern, simulated and measured at 12 gigahertz. This is 15 gigahertz. This is for 18 gigahertz. We see very good radiation property we observed. We can see the gain of the antenna can be from 12 to 18 gigahertz, can be from 26 to nearly 30 dB. So for this kind of antenna, we can have very good broadband and low side lobe and high efficiency. So this is a conclusion. I just mentioned that actually we can use a phase array to control both the amplitude and the phase of aperture, but that is very expensive because we have to use a phase shifter to control the phase. And the second disadvantage is that for phase array, it is narrowband, cannot be realized broadband. So thank you for your attention.
Thank you. About the first part, the anisotropic zero-index materials. So you use the mu to be zero in the propagation direction in the cylindrical and Cartesian case. But I would guess that would work as well if you have epsilon zero for that case.
Yes.
But wouldn't that be easier to get epsilon zero rather than mu zero?
So for epsilon or mu, that depends on the TE polarization or TM polarization. So if you use TM polarization, you can. So it's easy to get epsilon z equal to 0, no problem. For the 3D case, we have designed both epsilon near 0 and mu nearly 0.
Okay, but then continuing thing about then you had very broadband, I mean performance for the increase of the bandwidth of the antenna, but then I mean the mu 0 would be. I guess that is dispersive. So
sorry. For the first part, actually we cannot realize broadband because zero index is narrowband.
Yes, exactly.
But for the broadband is a lens antenna, metamaterial lens and a gradient lens.
Okay, so in the AZIM,
in the previous case, we realized a relatively broadband for the Verdi antenna because for the Verdi antenna, when we use homogeneous zero-index metamaterial, we can realize 1 gigahertz bandwidth. If we use graded isotropic zero-index metamaterial, we can realize 3 gigahertz bandwidth.
Okay, so it's sufficient that only at one part of the medium.
Yes.
Okay, thank you.
Thank you, Ari. Any other questions? Actually, just to follow up with that question, I had a question about your Vivaldi antennas.
Yeah.
Now, Vivaldi antenna is a very broadband
Yeah.
antenna. But when you put that structure inside, you mentioned, maybe you mentioned, or I missed that the bandwidth actually shrunk
Yes,
significantly, or no?
No. It's the same. The bandwidths are the same.
But the material, as Ari said, is dispersive.
Yes, but so this is very interesting because we measure many times. What I thought is in the design bandwidth it is okay, but it will destroy other bandwidth. But in fact, it's not.
It's not.
Yeah, it's not.
So Vivaldi antenna still keeps its bandwidth.
Yes.
That's very interesting.
Yeah, both the reflection coefficient and the gain in the radiation pattern.
Very nice. So we can talk about it more.
Okay.
Any other questions? If not, let's thank our speaker. Thank you.